Okay, this is a little video for my introductory calculus students, and I'm going to go through this problem. This is number 4G on the 4.1 assignment, and the actual question is to find the intervals where you were increasing and the intervals where you're decreasing. So all the examples I've done so far have been polynomials, and this one's not a polynomial, so I thought I better do one that works like this. Okay, as usual, when I'm about to do calculus, I use a red pen. Hang on a sec, let's fix that. There we go. As usual, when I'm doing calculus, I don't really want to work with a radical as much as I'd rather work with a fractional power. So there's my first step. And then I have to do the derivative of this, because remember, I know that I'm increasing over any interval where the derivative is positive, and I'm decreasing over any interval where the derivative is negative. So I need to do the derivative of this thing, so that's going to require a chain rule. So that's the derivative of the first thing times the second thing, plus the first thing times the derivative of the second thing. And there we go. So there's a nice little chain rule for us. Okay, I'm going to go back to radicals now. So this is just the square root of 4 minus x. And here I have an x that, oops, that's a plus sign. I'd have an x that remains in the numerator. And, this is times, everything's times by a negative, so I might as well just change that to minus. That takes care of this negative here. And then the denominator has a 2 in it and a square root of 4 minus x in it. Now, in some textbook exercises when we did chain rule, we kind of stopped there. But I need to do my interval check. And my interval check involves doing that chart where I examine factors. So I kind of want this thing to be in a factor form. It's really not that useful for me to have a term minus another term. I'd rather have something that was factors. So I'm going to do a common denominator. So if I do a common denominator, that would mean the common denominator is this denominator, because remember, this is just over 1. So the lowest common denominator here is 2 times the square root of 4 minus x. So I'll times this thing, oops, hang on a sec. I'll times this thing by 2 times root 4 minus x, which would be 2 times 4 minus x. Then minus an x all over my common denominator. Tidying that up, doing a little bit of algebra there, I'm going to get 8 minus 3x over 2 times 4 minus x. And remember that I am increasing over an interval where this thing is greater than 0. So when is this greater than 0? Oh, well, I'll just do algebra with that. I'll times both sides of the equation by this denominator, and I get this. So negative 3x is greater than 0. And then remember, we talked about this the other day. Oops, hang on. That's what I meant to write. Remember, we talked about this the other day. Algebra works the same with greater thans and less thans than it does with equals, but there's one extra rule you got to remember, and here it is. The next step to solve this equation is to divide both sides by a negative. What does that do? Right, it flips the sign of the inequality. So there we go. I know that we are we're going to be increasing when we're less than 8/3. And of course, then we could do the exact same algebra here for less than 0, and we get the same thing. We get 8 minus 3x is less than 0, so x would be greater than 8/3. Now, if you remember your notes, at this point you might be thinking, we're done. I know I'm increasing there, I'm decreasing there. No, we're not done. Because remember in your notes there was one other situation. Remember how Newton's theorem when it comes to this works? It says that I know I have a critical point or a critical value when the derivative is 0, which would definitely be at this 8/3. But what's the other time that you can have a critical value? When the derivative doesn't exist. And take a look. This is a square root. Right? We started right here at this thing. It's a square root. There's going to be places where this derivative doesn't exist. Specifically, this is going to have an end point. Right? Think about this. This is a continuous function up until you get to x being 4. And that's the absolute biggest number x can be. So what happens at 4? Well, it's just going to be an endpoint. So what's the derivative at an endpoint? Well, I don't have anything. So I'm going to say then that y primed does not exist if x is 4. Okay? And I wouldn't mind maybe even doing a quick interval chart on this to make sure I've got it done. Make sure I've got it proper. So my interval chart would be, okay, what happens when x is less than 8/3? So there's the first one. Then what happens when x is between 8/3 and 4? Because again, my other critical value is 4. And then what happens when x is bigger than 4? All right, now what are the actual factors here? We'll go back to where I was here. That is the two factors I'm going to worry about. Remember that when you divide factors, the integer rules work the same, right? Positive divided by a positive is positive. Same as when you're multiplying. So one factor is 8 minus 3x. The other factor is, I don't have to worry about this 2. 2 doesn't change the positivity or negativity of anything when you subtract it. So there's my other factor. Right? And then that tells me what the function's derivative is doing, and then that tells me what the function's doing. Okay, what happens? Give me a number that's less than 8/3. How about 0? 0 is less than 8/3. 0 would make this positive. 0 would make this positive. A positive divided by a positive is positive. So we are increasing from negative infinity up to 8/3. All right. Give me a number between 8/3 and 4. How about 1? 1's a number between 8/3 and 4. Oh, wait a minute. No, it's not. 1 is smaller than 8/3. 8/3. Okay, 8/3 and 4. Hang on a second. I gotta think about something. Maybe 9. Yeah, 3, I guess, would be a good number, right? 3. Let's use 3. 3 would make this thing negative. 3 would make this thing positive. A negative times a positive is negative. So we are decreasing from 8/3 to at least 4, maybe more. Let's see what's happening at 4. Well, at 4, if we go bigger than 4, we get 5. That makes this a negative. And aha, 4 minus 5 is negative, and you can't square a negative, so that doesn't exist. So that means that the derivative doesn't exist, and the function does not exist. So that would be your answer. This is what it'll say in the back of the textbook. Now, the name of this chapter is curve sketching, so I'm going to take this question a little bit further. What will this graph look like, and how did the derivative help me figure that out? Well, let's go back to a grid maybe. There we go. I got a nice little grid ready to go. I actually do have kind of a sense of what this graph looks like, and I'll explain that, how I know that in a minute. But let's start by, how about x and y intercepts? When would y be 0, and when would x be 0? Well, if x is 0, y is 0. So I know this point goes through 0, 0. So there we go, there's a point. Now, I just did the derivative and found out that 8/3 is where the slope is 0. And I actually know that that point will be, since I'm increasing to the left of it, and I'm decreasing to the right of it, right? Increasing, decreasing. It must be a peak. It must be a local maximum. Maybe it's even an absolute maximum. We'll find out. So let's see. So we are increasing to 8/3. So I got to find where 8/3 is. Okay, I'm going to guess where 8/3 is. 8/3 is, well, that's 3/3, 3/3, 6/3, and 2 more thirds. So somewhere around there. And then we know, okay, what is the actual value of that? I'll have to run that through my formula here. So if I have 8/3 times the square root of 8/3, whoops, wrong way, 4 minus 8/3. I had it backwards in my head for a second there. 4 minus 8/3. So that's going to be 8/3 times, let's see, 4 is 12/3. So 4/3. So I'm looking at something like 8/3 times 2 over root 3. Okay, ooh, what can I do with that? I need to graph this number. What can I do with this number? Well, I don't know. How about I rationalize the denominator, make my life easier? So that's going to be 16 over 3 root 3, but I'm timesing by root 3 over root 3. And so this is 16 root 3 over 3 times 3 is 9. So now I got to kind of have to estimate what that is. So 16 times root 3. Root 3 is somewhere around 1.7. So 16 times 16 is 256. So if I'm going 16 times 1.6, it'd be 225.6. So we're looking at around 25 divided by 9. A little under 3. Okay, so my answer here is 8/3, comma 16 root 3 over 9, which is, again, that is around 2.6, and this is a little shorter than, what did I say this was again? Around 2.5, something like that. So I'm going to go like that. Okay, so around 2.6, 1. It's 3.0. I didn't want to touch a calculator. Oh, yeah. What did I say earlier? I said it's around 3. So good enough. 1, 2, 0.5, 0.6, and then 1, 2, 3. So it's around here. I'll just make a big dot. There, that'll take care of it. What else do I know about this thing? I know that it has an absolute dead end if x is 4. So it literally can't go further than that. And if I wanted to have maybe one point, like what's it doing over in this range of the graph, or in this domain of the graph, whichever way you want to think about it. Well, you know what? I know that if I get another perfect square in this radical, I could figure out maybe another point. And let's see, if x was 0, I already got that point. How about if x was -5? Because x is -5, 4 minus -5 is 9, the square root of 9 is 3, 3 times -5 is -15. So -5, -15 is a point. And then, as x goes on and on and on forever, this thing's just going to get, to the left, it's just going to get smaller and smaller, and we already know to the right it's going to end there. So it's going to be some sort of curve like this. Something like that. And that's the curve sketching part. Notice I would have had no idea where this peak was without my calculus. Everything else, really, I was just using grade 10 and 11 regular graphing skills. I mean, even grade 7 skills. I did a table of values for that. Never underestimate your grade 7 table of values skills. When you're absolutely stuck, throw in some numbers, figure out where they go. Okay? Don't rely on it too much. It's a little unsophisticated, but it works. All right, let's see how close I am. I graphed it on Desmos this morning. Here is the graph. Okay, here's the points I picked, right? I picked 8/3, right? And then I picked 4, and then I picked 0, 0, and then the only other whole number I could think of was that one. And here's the actual graph itself. Pretty much what we picked. So there we go. That's the curve sketching. That's what we're heading towards. But between now and when we actually just end the unit, we have other skills and techniques we can learn for things that are even weirder than this. While I'm on the subject, though, of figuring out curves, do you remember back a few weeks ago, actually I guess now a few months ago, when we were doing limits? We had a worksheet where I handed you, and one of them was what's the limit of this thing as you approach infinity. And I actually said, well, we haven't really done sine and cosine graphs yet. You'll do that in grade 12. But I actually kind of know what this is going to look like, and I know actually that the limit's going to be 0. And the reason I knew that, I tried to explain this at the time, is that, well, I know what a sine curve looks like. Up and down, up and down, up and down, up and down. And I know what a 1 over x curve looks like. It's going to head towards the x-axis but never touch it as an asymptote. So when you give me the sine curve divided by x, you've kind of mooshed these two graphs together. So I kind of just looked at it and immediately went, yeah, it's going to be going up and down, up and down, up and down, but it's also going to be behaving like this thing and heading towards an asymptote of the x-axis. And that's the way you should think about complicated graphs. So when I'm looking at this one, I actually am kind of in my head thinking, let me get these points out of the way. I'm kind of thinking in my head, this thing is a y equals x, which is linear, and it's the square root of negative x, which is a curve like a half a parabola that goes that way. So this graph here kind of melds those characteristics together. So that's a useful way to think about complicated graphs. You might be looking at going, I've never seen a graph of an equation like that before. Yeah, but if you see the parts that make up that equation, you might go, oh, wait a minute. This part here is just a straight line. This part here is just a sideways negative parabola. And then this thing kind of melds those together. The mutant offspring of those two graphs is the way I like to think about it. All right, so that's all I wanted to talk about today. I can take some questions if anybody has them, but I'll end the video there. For all the band trip folks watching it, good luck with your homework.